So as you've seen from some of the previous squeeze theorem examples we've worked, that using the squeeze theorem to find limits involves paying very close attention to the directions of inequalities. And this is particularly the case when we're multiplying by quantities that can either be positive or negative depending upon whether we're considering the limit as x approaches from the right or from the left. In the previous video, we looked at this limit here, the limit as x approaches 0 of x cubed times the sine of 1 over the fifth root of x. And we noted that sine of anything, and in this case we have 1 over the fifth root of x, ranges between 1 and -1, or I should say between -1 and 1. But in the previous video, when we multiply each portion of the inequality by x cubed, depending upon whether x was approaching 0 from the left or the right, we'd multiply by either a negative number or a positive number, and multiplying by a negative number until the direction changed in the inequality. But when we multiply by a positive number, the direction of the inequality remained the same. And because of this, we had to consider the left and right limits separately. So we had to separately consider the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. In this video, we're going to be finding this same limit but using a different approach for which we don't have to separately consider the left and right limits. So looking at this compound inequality here, -1 is less than or equal to sine of 1 over the fifth root of x is less than or equal to 1. We can rewrite this as the absolute value of 1 over the fifth root of x is less than or equal to 1. And all this is saying is that this statement here is no different than saying that sine of 1 over the fifth root of x is always less than 1 unit from 0 on the number line. So if this is the number line and this dot is 0, and this is +1 here, let's say +1, and this is -1 here. Oh, that looks like a 7. Okay. That sine of x can be anywhere here in this region, including 1 and -1. And another way to say that is, sine of 1 over the fifth root of x can be anywhere in this region between -1 and 1. Another way to say that is, sine of 1 over the fifth root of x is always less than or equal to 1 unit away from 0. Now if we were to multiply both quantities on either side of this inequality sign by the absolute value of x cubed, let's see what happens. So on the left we'd have the absolute value of x cubed times the absolute value of sine of 1 over the fifth root of x. And on the right side we just have the absolute value of x cubed, because 1 times anything is itself. Here we have the product of absolute values. Well, that's the same thing. That's equivalent to the absolute value of this product here, x cubed times 1 over sine of the fifth root of x. And we'll just rewrite the right side here, absolute value of x cubed. So all this is saying is that the product of absolute values is equivalent to the absolute value of a product. And this inequality here is basically of the form, this is of the form absolute value of A is less than or equal to the absolute value of B. And we can draw a few conclusions from this, and I'm going to pick some numbers for A and B to show you the conclusion we can draw. So say A equals -5 and B equals -7. We just have to pick A and B such that the distance from 0 on the number line of A is less than the distance from 0 on the number line of B. Because absolute value is just the distance from 0 on the number line. So the absolute value of -5 is less than or equal to the absolute value of -7, right? So you can just put a semicolon here. The absolute value of -5 is indeed less than or equal to the absolute value of -7. But what we can say here is we can write these two inequalities here, and I'll write them and then explain them. So here, -5, which is A itself, is less than or equal to the absolute value of -7, but it's greater than or equal to negative the absolute value of -7. And this is basically the same thing as saying, well, A is less than or equal to the absolute value of B, but it's greater than or equal to the absolute value of -B. And I'll just draw two arrows here. These are equivalent statements. This is just for this particular choice of A and B. But also 5. We consider -5 is less than or equal to the absolute value of -7, but greater than or equal to the negative the absolute value of -7. But 5 is also less than or equal to the absolute value of -7, and greater than or equal to negative the absolute value of -7. So this is equivalent to saying that -A is greater than or equal to negative the absolute value of B, but less than or equal to the absolute value of B. Or alternatively, -A is less than or equal to the absolute value of B, but greater than or equal to negative the absolute value of -B. And really, this statement is also of this form, so we can draw two conclusions from this, right? So I'll just draw an arrow from here. So the first conclusion we can draw from this is that A here is x cubed sine of 1 over the 5th root of x is less than or equal to the absolute value of x cubed. It's greater than or equal to -B, which is negative the absolute value of x cubed. But we can also draw a conclusion about -A, the same conclusion about -A. -A here would be negative x cubed times sine of 1 over the 5th root of x. Well, -A is less than or equal to the absolute value or of b, which is in this case x cubed, but it's greater than or equal to negative the absolute value of b, which is in this case absolute value of negative the absolute value of x cubed. But what limit are we interested in finding here? We're interested in finding the limit as x tends to 0 of this quantity here, right? This boxed quantity here. So this is the compound inequality that we'll be working with. So what do we do with the squeeze theorem? How do we use the squeeze theorem here? Well, if we show that the limits of these two outside functions go to 0 as are 0 as x approaches 0, then we can conclude that the limit of this function, x cubed sine 1 over the 5th root of x, is 0 as x approaches 0. So that's what we're going to do. We're going to look at the limit as x approaches 0 of this function here. So the limit as x approaches 0 of negative the absolute value of x cubed. Well, that's the same thing as negative the limit as x approaches 0 of the absolute value of x cubed. And we know that's 0 because we will be taking smaller and smaller fractions, whether or not they're positive. When we cube them, when we take the absolute value of the result, they will end up positive. And so these fractions are going to get even smaller when we cube them, and as x gets closer and closer to 0, the cube of these fractions will get closer and closer to 0. They'll bear a negative sign if x approaches 0 from the left, but when we take the absolute value, that negative sign will disappear. So whether or not, so when you cube, let's say x equals, I don't know, 1/5. So positive, let's say we're looking at, x equals 1/5 and x equals negative 1/5. When x equals positive 1/5, you cube it, you get 1 over 5 cubed, which is 1 over 125. Take the absolute value of it, you still get 1 over 125, and negative of that is negative 1 over 125. But what's the deal with the negative case? So x being negative 1/5, you cube it, you get negative 1 over 125, but you're taking the absolute value. So once again, you will get a positive number. You take the negative of that, and you get negative 1 over 125. So the same deal as in the positive case. So this limit is 0. But also, the limit as x approaches 0 of this function, the absolute value of x cubed, is 0 as well. And so, by the squeeze theorem, I'm going to abbreviate that THM, the limit as x approaches 0 of x cubed sine of 1 over the 5th root of x, this is kind of messy, just rewrite it here, sine of 1 over the 5th root of x is equal to 0. And notice here we didn't have to evaluate the left and right limits separately, and that's because for these outside functions we had absolute values on them. So regardless of whether x was positive or negative, and that means whether or not we were approaching 0 from the right or left, when you cube and you take the absolute value of that result, you will get the same answer when dealing with a quantity or its additive inverse. So we were able to avoid having to deal with left and right limits, and and we got the same answer as we did in the previous video when we did use left and right limits. So hopefully that shows you how absolute values can be used to avoid having to take left and right limits when approaching from the left and approaching from the right would otherwise entail a direction change in the inequality. Would entail a direction change in the inequality when you're dealing with a when you're multiplying by a negative number, and not entail one when you're multiplying by a positive number. The absolute value helps you get rid of that difference there.